Hello everyone, welcome back to the online classes by Konnur institutions. In last class we were discussing about the vapor pressure of solid in liquid and also lowering vapor pressure, and also one more is relative lowering vapor pressure. So I will remind you what we taught in the last class in 5 minutes. So vapor pressure of solid in liquid, here the solute is taken as a solid and solvent is taken as a liquid, but the nature of the solute is non-volatile. Nature of the solute is non-volatile, it means it will not evaporate to form the vapor molecules, and the solvent is a volatile nature. So if we add the non-volatile solute to the volatile liquid, so what about the vapor pressure of the solutions, as we already discussed that. So when non-volatile solute is added to the solvent, the vapor pressure is decreases. The decreased vapor pressure is because of the non-volatile solute. So that is the P1 naught is greater than the P1 we will call. So in case of that, one more you have to remember, the decreased pressure is directly proportional to the amount of a solute dissolved in the solutions. That you have to remember. And one more, lowering vapor pressure we will discussing, that is difference between the vapor pressure of the pure solvent and that of the solution is known as a lowering vapor pressure. And one more is relative lowering vapor pressure, that is the ratio between the lowering vapor pressure of the solution to the vapor pressure of the pure solvent. So that this much we discussed in the last class. And general formula of the Rod's law, we can modify the Rod's law like this: for any solution, the partial vapor pressure of each volatile component in the solution is directly proportional to the mole fraction. When we added a non-volatile solute, so whatever the vapor will come, that is because of the volatile component present in the solutions, that we are directly proportional to each other. For any solution, the partial vapor pressure of each component in the solution is directly proportional to the mole fraction. This is the general formula of the Rod's law. In today's class, we will discuss about the classification of a liquid solution on the basis of Rod's law. Those are now we'll discuss now. Classification of liquid solution based on Rod's law. This is important for the examination point of view. That is a liquid solution we were discussing. One is a solid is act as a liquid and solvent is also act as a liquid here. So now in case of this one, this can be classified into two types. One is a ideal solution, another one is a non-ideal solution. So one classification, that is ideal solution, another one is non-ideal solution. The question arises here, what do you mean by the ideal solution and non-ideal solution? Now we'll discuss that. The ideal solution means the solution which obey the Rod's law at an entire range of concentration. Such type of solutions are known as ideal solutions. The solutions which does not obey the Rod's law at an entire range of concentration, that is known as non-ideal solutions. Ideal solutions can obey the Rod's law. So the solution which obey Rod's law at entire range of concentration. This type of ideal solutions which obey the Rod's law, it means ideal solutions can be formed when the mixing of two components having a identical molecular size and identical structure, and also that should have a almost similar intermolecular force between the solution and the pure components. In such cases, the ideal solutions which obey the Rod's law. So that type of solutions are ideal solution. Non-ideal solutions means the solutions which does not obey Rod's law. Rod's law at entire range of concentration. Entire range of concentration. And next one, in case of ideal solutions, when we mix the two liquids, one is the solid is act as a liquid here and solvent is also act as a liquid. When we add the two liquids, the solution will be formed. In such cases, the delta HR change in enthalpy after mixing is 0. There is no change, means no heat is liberated or no heat is absorbed when we mix the two liquids in a particular beaker. So for example, you can take the one liquid I will take. So that is one liquid, say it is A, and another liquid I will take, so that is also taken as B. So this liquid is a pure component, this liquid having a AA type of interaction between the molecules, and here BB type of interaction between the molecules. When we add this A to the B, the solution will be formed. When we add these two, the solution will be formed. Again, new interaction will be arises here, that is the AB interactions when we add the A to the B. So now the new interaction here, for example, if the new interactions are formed, means A reacts with the B, AA reacts with the BB, so that is AB interactions are formed. Two molecules of AB, that is AB interactions are formed. If the new interactions will be formed, means earlier bond should be broken. Here we have to break the bond, this one. So if you want to break this bond, means need energy, we have to give the energy. In such cases, say the example is like 20, we need energy to break this bond, and so here also same liquid having the same interactions. Here also we need this much energy to break the bond. So total, if we giving a energy in the sense that is a endothermic, so that is a positive, total amount will be 40. Here you can take so 2 into new interaction will be formed, so that is a AB. So how much you can say, that is a 20. Here amount of energy will be released in the sense that is denoted by the exothermic negative, so that is total is 40. So amount of energy required to break the bond and amount of energy released after the new bond formations taking place, so is equal. In such cases, we are telling that ideal solutions, that is the change in enthalpy, delta in the sense change, H in the sense enthalpy. Change in enthalpy after mixing the components. After mixing the component is 0. In the sense what it is? No heat is liberated, no heat is absorbed in the reaction. So that is the meaning of delta H mixing is 0. But in case of non-ideal solutions, that is the delta H mixing is not equal to 0. Not equal to 0. It means if some amount of energy will be released here or some amount of energy will be absorbed. So later we will discuss in detail about the non-ideal solutions. And one more point you can remember regarding the ideal solutions. So the delta V, in the sense what? Change in volume after mixing. Change in volume after mixing is equal to 0. Means total volume of the solution is equal to the individual value here. So for example, you can take when we add say 100 cm cube, you can take. When we add the 100 cm cube of A to the 100 cm cube of B to the one beaker, the solution will be formed. How much we are expecting? 100 and 100 is equal to 200 cm cube. Same. Here also the volume of the solution is equal to the sum of the individual volume of the two components, that is equal to 200. There is no change in volume after the mixing. So that is the meaning of delta V mixing is equal to 0. But in case of non-ideal solutions, that is a delta V mixing is not equal to 0. It means what? When we add the one solute, one liquid to the another liquid, so we are expecting 200 here. 100 cm cube is added to the another 100 cm cube. We are expecting 200 in case of ideal solutions. But in case of a non-ideal solution, it may be the 200. Example we have taken. It may be the 200 or may not be the 200. More than 200 or less than 200. That we are termed as a change in volume after the mixing is not equal to 0 in case of a ideal solution. And one more you can remember here, according to the Rod's law, the total vapor pressure of the solution. Total vapor pressure of the solution is equal to the what? Sum of the partial pressure of the components present in the solution. That is a P total is equal to P1 plus P2. But in case of a non-ideal solution, the total pressure of the solution may not be equal to the P1 plus P2. P1 plus P2. It may more than that or less than that. Later we will discuss about that. So, and here delta H mixing is not equal to 0. I written equal to 0. So just you correct this one, not equal to 0. And one more point you can remember regarding the ideal solution is interaction between AA and BB is almost equal to the AB interactions. But in case of non-ideal solutions, the AA and BB interaction is not equal to AB interaction. It may be the more than AB or less than AB. Now we'll discuss the classification of non-ideal solution based on the positive deviation and negative deviation on the basis of vapor pressure. Yes, according to the Rod's law, the non-ideal solutions doesn't having a vapor pressure equal to 0. It may be the more vapor pressure as we predicted by the Rod's law or less vapor pressure as we predicted by the Rod's law. So now classification of non-ideal solution based on the vapor pressure, that is the non-ideal solution showing a negative positive deviation and a non-ideal solution showing the negative deviation. So which type of a solutions will show the positive deviation and which type of a solutions will show the negative deviation? Now we will discuss that. So if the solutions of the non-ideal solution showing the positive deviation means the solution having a higher vapor pressure than predicted by the Rod's law. It means observed vapor pressure is more than the vapor pressure predicted by the Rod's law. So here the solution or the observed vapor pressure is more than vapor pressure predicted by Rod's law. Vapor pressure predicted by Rod's law. And here non-ideal solution showing a negative deviation means observed vapor pressure is less than vapor pressure predicted by Rod's law. It means if in case of a positive deviation, AB interactions are weaker than the AA and BB interaction. What it means, AB and BB means we have taken two liquids here. Liquid solution is one, we have taken a liquid A that is having a AA interactions, and if we have taken a one more, that is a BB interactions, one more liquid that is having a BB type of interactions. When these two liquids are mixed, the solution will be formed. So that is having a new type of interaction, that is a AB interactions. If in case of a non-ideal solution showing the positive deviation, AB interactions are weaker than the AA and the BB interaction. So interaction between the AA and BB, what it is? AB interactions are less than the AA interaction and BB interactions. What happens if the interaction of AB will be less than AA and BB? how the vapor pressure is more than what we expected from the Rod's law. If the AB interactions are weaker, if the AB interactions are weaker means tendency to escape this AB will be increases from the solution. If the tendency to escape from the liquid phase to vapor phase means more vapor pressure will be there because it is having a less or weak interaction between the AB. If the more vapor pressure is arises above the solution means it will exert a more pressure on the solution. Hence we are expecting the more vapor pressure as we expected for what it is by the Rod's law. Hope you all are getting this one. Here the AB interactions are weaker than AA and BB. If the AB interactions are weaker means tendency to escape liquid phase to the vapor phase is increases because the interactions will be weak. If it is escaping tendency will be increases means more vapor pressure will be observed on the solution. If the more vapor will be there, that will exert the more vapor pressure on the solution. Hence, we are having a more vapor pressure than what it is vapor pressure predicted by the Rod's law. And in case of this one, the observed vapor pressure is less than the vapor pressure predicted by the Rod's law. Here the AB interactions are stronger than AA and BB. AB interactions are stronger than AA and BB. So if it is, when we add the two liquids, the solution will be formed. In such cases, means a non-ideal solution showing a negative deviation. AB interactions are stronger means a tendency to escape from the liquid phase to the vapor phase is less. It means less vapor molecules are collected over the solution. Those less vapor molecules will exert a less pressure on the solution. Hence, we are expecting the less vapor pressure than predicted by the Rod's law. And non-ideal solution showing the negative deviation having a, that is a change in enthalpy after mixing. Change in enthalpy after mixing is greater than 0. What it means greater? It is not equal to 0. If it is equal to 0 means that we are calling as a ideal solution. So change in enthalpy after mixing is not equal to 0. It is more than 0 means no. So if it is more than 0 means that is in case of a positive only. Positive in the sense endothermic reaction will occur. So that is endothermic process will be there. Endothermic. So that is positive. More than 0 in the sense positive will be there. Delta H mixing is greater than 0. But in case of this one, here delta H mixing change in enthalpy is less than 0. It means what? Process is exothermic reaction. Less than 0 means negative will come. Negative in the sense energy will be negative in the sense that is a exothermic process. Here the delta mixing is greater than 0 means we have to give the energy to break the AA and BB. We have, because AB interactions are weaker in case of a positive deviation solutions. AB interactions are weaker means we have to give the more energy to break these bonds. If we are giving a more energy in the sense that it should be in a positive, that is a endothermic process we are calling. So next one, non-ideal solution showing the positive deviation means a change in volume after the mixing. Change in volume after the mixing is more than 0. So it means total volume of the solution is more than the what it is pure components. Example you can take when we added A to the B or A liquid and B liquid added to the one container, the AB interaction will be formed. In case of non-ideal solution showing a positive deviation means these two interactions between the AB will be weak in the sense those having a weak interaction between the A and B. If it is a weak interaction means volume will be increases. So volume will be increases means that is more than the what it is delta V is mixing is more than 0 means total value will be increases. If it is So if we are adding the A to the B means AB interactions are stronger. So interaction between A and B molecules are very tightly held. If it is a tightly held in the sense total volume will be decreases. Hence we are writing in case of non-ideal solution showing the negative deviation. Change in volume after mixing is what it is? Less than 0 because of the more interaction or more attraction between the A and B leads to the decrease in the volume in case of negative deviation. Example for the non-ideal solution showing the positive deviation are ethyl alcohol and cyclohexane, acetone and benzene, and acetone and ethyl alcohol, CCl4 and CHCl3. In case of this one, non-ideal solution showing the negative deviation, phenol and aniline, chloroform and benzene, acetone and chloroform, H2 and HCl. These mixture will show the negative deviation and this mixture will show the positive deviation. So now, and also one more difference you can remember here. In case of non-ideal solution showing the positive deviation, the total vapor pressure of the solution is not equal to what it is? The compound vapor pressure of components. Now it is the P total is more than the P1 plus P2 partial vapor pressure of the components present in the solution. In case of negative deviation solutions, that is a P total is equal to, P total is less than the partial vapor pressure of the components present in the solution. So now we'll explain one example regarding the non-ideal solution showing a positive deviation, how the vapor pressure will be more than predicted by the Rod's law. Example, you can take the ethyl alcohol and cyclohexane. So ethyl alcohol having a hydrogen bond between the another ethyl alcohol molecule. I will write the ethyl alcohol here. So now example it is ethyl alcohol plus cyclohexane. So now I will write the ethyl molecule, ethyl alcohol, that is C2H5OH, and one more ethyl molecule I will write C2H5, and one more ethyl molecule C2H5. So it is AA type of interaction. Here oxygen is more electronegative, so that is a delta negative. Here it is delta positive. In case of this one also, oxygen is more electronegative, hydrogen is less electronegative, that is a delta positive, this is a delta negative. Here there is an interaction between the hydrogen atom and more electronegative element like oxygen, nitrogen and fluorine. There is a formation of hydrogen bond taking place. Here the ethyl alcohol molecules having a hydrogen bond between the another ethyl alcohol molecule. So when we add the cyclohexane to the ethyl alcohol, when we add the cyclohexane to the ethyl alcohol, cyclohexane will occupy the place in between the ethyl alcohol. When it is the place in between the ethyl alcohol means the hydrogen bond present in the ethyl alcohol will be broken. When the hydrogen bond will be broken in ethyl alcohol means the interaction between the ethyl molecule will be decreases. If it is a decreases in the sense tendency to escape the alcohol molecules from the solution is increases. If it is easily escaping from the solution means more vapor pressure will be produced in the solution. If it is ethyl alcohol will be weak. When it is a broken means tendency to escape the solution from the solution is increases. Hence more vapor pressure will be observed as we predicted from by the Rod's law. This type of solutions are showing the positive deviation, that is a non-ideal solution showing the positive deviation. In such cases, when we add the cyclohexane to the ethyl alcohol, AB interactions will be weaker. AB interaction will be weaker than AA and BB. AA and BB. So AA means, for example, ethyl alcohol having a strong hydrogen bonding. When we add another cyclohexane to this one, the bond will be broken here, hence the interaction will be less than A and BB. If the interaction of this one is decreases or weakened, means tendency to escape from the solution is increases, hence we are expecting more vapor pressure as we predicted by the from the Rod's law. And the next one, non-ideal solution showing the negative deviation you can take. So you can take the acetone and chloroform, acetone and chloroform. Acetone and chloroform. See, what is the molecular formula of acetone here? That is CH3 C double bond O CH3. This is called as acetone or propanone. And chloroform, that is CHCl3. This is chloroform. So when we add the acetone to the chloroform, after the addition of acetone to the chloroform, there is a hydrogen bond taking place between the what? Acetone and the chloroform. So this is the delta negative, this is a delta positive. So compared to carbon and oxygen is more electronegative, hence we have to take the delta negative. Carbon is less electro, that is a delta positive. Here delta negative, delta positive. There is an interaction between the delta negative and delta positive, between the hydrogen and the more electronegative, that we are calling as a hydrogen bond. So after the addition of hydrogen bond, after the addition of chloroform to the acetone, there is a formation of hydrogen bond taking place. It means escaping tendency of A and B will be decreases, because after addition hydrogen bond is taking place. If the escaping tendency of A and B will be decreases in the sense a less number of vapor molecules are formed over the solution. So this is a AB interaction after the addition. So there is a hydrogen bond. If it is having a hydrogen bond, more attraction means a tendency of escaping from the solution to the vapor phase is decreases. It means less number of vapor molecules are formed over the solution. Those vapor will exert the less pressure on the solution side. Hence the total vapor pressure of the solution is less than the vapor pressure predicted by the Rod's law. Such type of solutions are showing the negative deviation, means less than the vapor pressure predicted by the Rod's law. And you can take the one more, phenol and aniline also. Phenol, that is a benzene attached by the OH, and aniline, so that is NH2. After the addition of phenol to the aniline, so there is a formation of hydrogen bond taking place between the oxygen and the nitrogen. Hence the AB interaction will be stronger. Tendency to escaping from the solution is decreases. Hence we expecting a less vapor pressure as we predicted by the Rod's law. So this type of solutions will show the non-ideal solution showing the negative deviation. Very important for the examination point of view. You have to remember the examples and the explanation regarding this one. Yes, let us draw the graph for the non-ideal solution showing the positive deviation. So there are two components. We have to draw the two graphs for the two components. This is the one axis, and another components, another axis I will take. This is the one more axis. So we are vapor pressure versus mole fraction. Vapor pressure versus mole fraction. For the component 1 that starts with the origin, it means x1 mole fraction of first component is 0. So that is, so we are having a vapor pressure is increases, means mole fraction is also increases. So that maximum value of first component will be P1 naught. So this is P1. And mole fraction of second component, so maximum value is 1, it is x1 is equal to 1. So now second component, x2 is equal to 0, it starts with the origin. As the vapor pressure is increases, so mole fraction of the solution is also increases, that is a maximum value is P2 naught, X2 is equal to 1. Sum of the mole fraction of components is equal to 1. Sum of the mole fraction of the components is equal to 1. If you add the total vapor pressure of the solution, we have to do the sum of the partial vapor pressure of the components, that is P total is equal to P1 plus P2. This is the graph for the Rod's law. So now non-ideal solution showing the positive deviation. It means the total vapor pressure of the solution is more than the vapor pressure predicted by the Rod's law. More than this means this is having a more vapor pressure because of the interaction between the AB is less than the A and BB. Hence a more vapor pressure we are expecting. Here also in second cases more vapor pressure are expecting. If it is a partial vapor pressure of the two component is more, means the total vapor pressure should be more. So hence it is more than vapor pressure predicted by the Rod's law. This is a graph for the non-ideal solution showing the positive deviation. And coming to the point, non-ideal solution showing the negative deviation. So that is, we have to draw the graph for the two components, two axes we have to take same. So now this is a vapor pressure versus mole fraction. Same, ideal solution is x1 is equal to 0, here x1 is equal to 1, as we already discussed this one. x2 is equal to 1, here x2 is equal to 0. Sum of the two components. First component vapor pressure according to the Rod's law I will draw here. So this is the maximum value is P1 naught and this is maximum value is P2 naught. This is P2, this is P1. If you want the total vapor pressure, the sum of the partial pressure of the two component is equal to P total is equal to P1 plus P2. According to the non-ideal solution showing a negative deviation, AB interactions are stronger than A and BB. It means escaping tendency of AB will be less. It means less vapor molecules are formed over the solution, less vapor pressure as we expected from the Rod's law. So it is a less vapor pressure than the vapor pressure predicted by the Rod's law. Second component, less vapor pressure predicted by compared to the predicted by the Rod's law. Here also total vapor pressure will be less than the vapor pressure predicted by the Rod's law. This is the graph between the non-ideal solution showing positive deviation and non-ideal solution showing a negative deviation. Very important for the examination point of view. You have to remember the examples regarding this one and also how it will be the positive deviation and the explanation regarding that we have to remember. So next part of the solutions we will discuss in the next videos. So see you. Thank you.